Hello everyone, my name is Mohit Gupta and I welcome you to my YouTube channel Cam Fundamentals. Today we are going to discuss Equilibrium Part 2. The Part 1 and the rest of the parts are given in the description box as well as in the I button over here. So without further delay, let's get started. Today we are going to discuss Law of Mass Action, Law of Chemical Equilibria, the equilibrium constant Kc and Kp, how to derive relationship between Kp and Kc, and at the end we'll be talking about the characteristics of equilibrium constant. So first let's start with the law of mass action. The rate of a reaction is directly proportional to the product of the active masses of the reactants. Okay, not on the product, on the reactant raised to the power of their stoichiometric coefficients in a balanced chemical equation. So first of all, let's discuss what is active masses. So active masses is nothing, just the molar concentration of the reactant, and it is denoted in the square brackets like this. So what is molar concentration? Molar concentration, also known as molarity, which is defined as the number of moles of solute dissolved in 1 liter of the solution. So molarity is equal to the number of moles of the solute divided by the volume of the solution, and it should be in the liter. The units of molarity is m, capital M, and it can also be written as mole per liter. So let's take an example. This is your balanced chemical equation. 2a plus 3b is giving us A2B3. The stoichiometric coefficients of the reactants are 2 and 3, and the stoichiometric coefficient of the product is 1. Since nothing is written here, we can say the stoichiometric coefficient of the product is 1. So from the law of mass action, we can see the rate of a reaction is directly proportional to the active masses of the reactant, that is its molarity of the reactant. So we can write down the rate of reaction. For this reaction, the rate of reaction is directly proportional to the concentration of A or the molarity of A, and since we have two molecules A, we can say the rate of reaction is directly proportional to the concentration of first molecule, concentration of the second molecule of A, and since we are using 3 moles of B, we can say the rate is directly proportional to the first B, second B, and third B. And in short, the overall rate is directly proportional to the A raised to power 2 and B raised to power 3, where 2 and 3 are the stoichiometric coefficients of the A and B respectively. Let's take one more example to make the concept a little more clear. Here we have taken a general reaction A plus B is giving us AA and BB, where small a and small b are the stoichiometric coefficient of the reactants A and B respectively, and the stoichiometric coefficient of the product is 1 here again. So here we can write down that rate is directly proportional to the concentration of A raised to power A and concentration of B raised to power B. Let's move to the law of chemical equilibria. In last case, we have seen the law of mass action. Now, when the law of mass action is applied to the reversible reaction, then it is converted into law of chemical equilibria. So it extends the law of mass action to the reversible reactions. What are reversible reactions? Those reactions which occur in both the direction, in forward as well as in the backward, which means the reactants are converting into the product and product is converting back into the reactants. So let's take an example of reversible reaction. 2a plus 3b is giving us A2B3. We have taken the same equation. Here the reaction is reversible. The products are getting converted into the reactant and reactant is getting converted into the product back. So in this case, we have two directions, a forward direction and the backward direction. So rate of forward direction is dependent upon its reactant. The reactants are A and B. So it is directly proportional to the concentration of A raised to power 2 and concentration of B raised to power 3. Now here in this case, rate is equals to the Kf A raised to power 2 B raised to power 3. Here we have removed the proportionality constant and we have substituted with the equal to, and in order to do so we have to place a constant over here. Similarly, rate of backward reaction is directly proportional to the reactant, and for the backward direction the reactant is A2B2, and since its stoichiometry is 1, therefore we will put 1 here, or we won't put anything here. In order to remove this proportionality constant, we have to place a constant where we have placed the Kb, where Kb is the constant for the backward reaction, and now we can replace proportionality constant with the equal to sign. Now one thing we know already, that at equilibrium the rate of forward direction is equal to the rate of backward direction. So in that case, the rate of forward direction, which is equals to Kf A square B cube, is equals to the Kb A2 B3. So let's substitute here. On substituting, we can divide Kf divided by Kb, which is equals to A2B3 divided by A square divided by B cube. Now we have one constant here and we have one constant here. So on dividing two constant, what we'll get? A new constant. So this new constant is considered as equilibrium constant. Now one thing is important here, that K is the equilibrium constant, and by convention the active masses of product is written in the numerator and the active masses of the reactant are written in the denominator. We can also write it like Kb divided by Kf, and which is equals to A square B cube divided by A2B3. However, by convention we always write like this only. The concentration of product is always in the numerator and the concentration of reactants is always in the denominator. So let's take one general reaction. AA plus BB is giving us CC and DD, where small a, small b, small c and small d are the stoichiometric coefficients of the reactant and the product respectively. In this case, we can write down the equilibrium constant like C raised to power C, D raised to power D, A raised to power A and B raised to power B. Now what does C means here? This C denotes the concentration terms because we are taking the molarity or the active masses, so we are writing C, that is concentration term. So this is your law of chemical equilibria, and K remain constant at constant temperature. This is very important point, that with the change in the temperature, the volume of the solution changes and hence the molarity of the solution changes, due to which the equilibrium constant also changes. So equilibrium constant is always constant at constant temperature. If we increase or decrease the temperature, the equilibrium constant also changes. Now what is equilibrium constant? We can define the equilibrium constant like it is the ratio of concentration terms of product. We have product here, so it is the ratio of concentration of the product raised to power their stoichiometric coefficient to the concentration term of the reactant raised to power their stoichiometric coefficients, but the reaction has to occur at constant temperature. Now Kc is used to express the concentration terms, and similarly we also have Kp. Here Kp is used for the gaseous reaction. Whenever we don't have concentration terms or the reaction is occurring in a gaseous phase, then we use Kp to express the equilibrium constant, and we use partial pressure of the reactants and products. So let's take one more example. AA plus BB is giving us CC and DD, and if I assume that all the reactants are gases, then in that case I can write down Kp, which is equals to the partial pressure of the C raised to power its stoichiometric coefficient C, partial pressure of D raised to power its stoichiometric coefficient D, partial pressure of A raised to power its stoichiometric coefficient A, and partial pressure of B raised to power its stoichiometric coefficient B. So let's discuss the relationship between Kp and Kc. So in case if you are given Kp and you have to find out the Kc for that reaction, you can easily find out with the relationship formula of Kp and Kc. For this we'll be taking a common reaction. AA plus BB is giving us Cc and Dd. So for this we can easily write down Kc, which is equals to the concentration term of C and D raised to power their stoichiometric coefficient divided by the reactant and their stoichiometric coefficient. So let's write it down as equation 1. Now we'll write down the Kp, formula of Kp. We have seen it already. Now we will be using the ideal gas equation. What is ideal gas? Pv is equals to nRT, where P is the pressure, V is the volume, R is the gas constant and T is the temperature, and N is the number of moles. So I can also write it as, or rearrange it as, P is equals to N by V RT, where N is the number of moles and V is the volume. So if you remember the formula of molarity, which was number of moles of solute dissolvent, volume of solution. So here we can write it down like number of moles are here and volume is here. So I can easily replace it with the concentration. So N by V can also be written as C, molarity. So therefore P is equals to CRT, where C is the concentration term. Now for each reactant I can write it down. PA is equals to CART, PB is equals to CBRT, PC is equals to CCRT, and PD is equals to CDRT. Now what I'll do, I'll substitute the equation 4 into the equation 2. Now I'll substitute the pressure term, and I will try to relate the Kp with the concentration term. And in order to do so, I'll write down Kp is equals to CCRT, CDRT, CART, CBRT raised to power their stoichiometric coefficient. Now this is your equation 5. Since RT is common everywhere, I can remove the RT and put it here. Now I can write it down like C plus D, and same in denominator RT raised to power A plus B. Now on further rearranging, I can write it down CC raised to power C, CD raised to power D. This is all same, and RT C plus D minus A plus B, because it is in denominator. When it come up upside, it will be in negative. So this is your equation 7. Now what I'll do, I'll substitute the equation 1 in equation 7. Moreover, C plus D is the stoichiometric coefficient of the product minus stoichiometric coefficient of the reactant. So it is the number of moles that are changing from going product to reactant. So we can write down delta N is equals to C plus D minus A plus B, which is the change in the number of moles. So we can write number of moles of gaseous product minus number of moles of gaseous react. One point you need to remember here, that you don't have to include any liquid or solid here, because the volume change in the liquid or the solid is very less, because they are very much incompressible. So moving further, we can say Kp is equals to Kc. This is your Kc into RT raised to power delta N, where delta N is the change in the number of moles. Here we use R, and the units of R is liter bar per mole per Kelvin. The value of R is 0.0831 liter bar per Kelvin per mole. There is one more value of R is 8.314 joule per Kelvin per mole, but we are not going to use here because we have volume term as well as the pressure term. Moreover, 1 bar is equals to 10 to the power 5 Pascal, and which is equals to 10 to the power 5 Newton per meter. And if we have to change the bar into ATM, we can do it using 1 bar is equals to 0.987 ATM. You have to remember all these units, okay? Because in most of the cases the pressure would be given in the ATM, and you have to convert it in the bar, because you are be using R as 0.0831 liter bar per Kelvin per mole. Okay, so here we can see if delta N is equals to 0, that is the number of moles of gaseous product is equal to the number of moles of gaseous reactant, then RT raised to power 0 would be equal to 1 and Kp would be equal to the Kc. If delta N is the positive, which means the number of moles of product are more than the number of moles of the reactant, in that case Kp would be greater than Kc. Cool. If delta N is negative, in that case the Kp would be lesser than Kc, which means the number of moles on the reactant sides are greater than the product side. So let's discuss one important question. What is the value of Kc for the following reaction at 700 Kelvin with Kp is equals to 1.80 into 10 to the power minus 3 kilopascal? The reaction is given twice of NaCl, which is decomposing to give twice of NO plus chlorine gas. Now in this case, we have to determine the Kc, and what we are going to use, we are going to use this formula Kp is equals to Kc RT raised to power delta N. We have Rp here, we can find out delta N. How? Like this, delta N is equals to 3 minus 2, which is 1 mole. The number of moles in product is 2 plus 1 is equals to 3, and on the reactant side we have 2, so delta N is equals to plus 1. Now we will substitute these value in the formula of Kp and Kc. In that case, we can write down Kc is equals to Kp RT minus delta N. So let's write it down. Kp is 1.8 into 10 to the power minus 3, and we have kilo, which is equals to 10 to the power 3. So 10 to the power minus 3 will be get cancelled out by the 10 to the power 3. So it is 1.80 Pascal. The value of R I have written here. So here you have Pascal and here you have bar. So you know 1 bar is equals to 10 to the power 5 Pascal. So 1 Pascal is equals to 10 to the power minus 5 bar. Okay, and into 700 Kelvin. So 1.80 into 10 to the power minus 5 bar. From bar you can cancel out the bar. From Kelvin you can cancel out the per Kelvin. And at the end you will be having these units. So on substituting all of these, on dividing and multiplying, what we'll get, Kc is equal to 3.09 into 10 to the power minus 7 mole per liter. This is a very simple question. Now we'll be talking about the characteristics of chemical equilibrium. So first of all, as I have already told you, the equilibrium constant is dependent on temperature. Why it depends upon the temperature? Because on changing the temperature, the volume of the solution changes. And if the volume of the solution changes, the concentration term of the reactant as well as of the product changes, which results in the different value of the equilibrium constant. Moreover, it is also independent on the initial concentration of the reactant and product. So whatever is the initial concentration, it doesn't matter. So equilibrium only deals with the concentration term of the reactant and product at equilibrium. Okay, so if the reaction is reversed, then the value of new equilibrium constant is also reversed. What does it means? Let's see. So for this reaction, twice of NaCl giving us twice of NO plus Cl2, we can write Kc is equals to Cl2 into concentration term of NO raised to power 2 and in the divided by concentration of NoCl raised to power 2. Now if I reverse the reaction, then these would be the reactant and this would be the product. So this would be my new equilibrium constant. So NoCl raised to power 2 divided by C2 divided by NO raised to power 2. So what is the relation between the two? The Kc and Kc prime are reverse of each other. So if you reverse the reaction, the value of equilibrium would be 1 by old equilibrium constant. So if you have a reaction and if you divide it by the 2, then the equilibrium concentration won't be divided by 2. It would be under root of the old equilibrium constant. So in order to explain that, I have taken this reaction and I have divided it by the 2. So it will become 1, it will become 1 and it will become 0.5 or 1 by 2. Okay, so if I have to write down the equilibrium constant, what I can write, Cl2 raised to power half, NO raised to power 1, NoCl raised to power 1. Now if I take under root of this Kc, what I'll get, I'll take 1 by 2. So after doing so, what I'll get, Cl raised to power 1 by 2, NO 2 into 1 by 2, which is equals to 1, and here also 2 into 1 by 2 is equals to 1. So this way what I'll get, the Kc prime is equals to under root of Kc. So if you are dividing the equilibrium reaction with n number, then what you will have to do, you have to take the under root nth time. Okay, if you are multiplying the equilibrium constant by 2, you have to take it square. So here I have taken the same reaction and I have multiplied with the 2. Then it becomes 4 of NoCl is giving us 4 of NO plus twice of Cl2. So if you write down the new equilibrium constant, you will get square 4 and 4, and in the last case you have 1 square square. So if you will take the square common, what you will get, you will get the Kc back. Okay, so if the reaction is multiplied by the n, the equilibrium constant of the new reaction would be raised to power n. Moreover, if you have two equations and you are trying to add them, then their equilibrium constant would be multiplied, not added. What does it mean? So for this reaction, I have taken A is converting into B. For this, the equilibrium constant would be B by A. For another reaction, I have taken B is giving us C. In this case, K2 is C by B. So if I'll add this reaction, the B would be cancelled out by this B and the overall reaction would be A is giving us C. In this case, K is equals to C by A. It's obvious. How will I get C by A? If I'll multiply K1 and K2, what I'll get? B by A into C by B, which is equals to C by A. And C by A is what? Is your equilibrium constant for the final reaction, which means if you are adding two reactions, you have to multiply them, and if you are subtracting two equations, you have to divide them. The next point is the equilibrium constant is not affected by the addition of the catalyst. So whether you add a promoter or a catalyst, the equilibrium constant, the value of equilibrium constant won't be changed. Why? Because catalyst increases the rate of the forward direction as well as it increases the rate of backward direction. To sum up, I can say that if I reverse the reaction, then I have to divide it. If I divide the reaction by n, I have to take under root n times. If I multiply the reaction by n, I have to write down the n in power. If I add two equations, I have to multiply them. Okay, so there is one more question. Find out the value of Kc for the following equilibria. So I have given you the reaction, these two reaction where the Kp value of Kp is given at different temperature, and you have to find out the value of Kc. How will you find out? We will use the same equation, Kp is equals to Kc RT raised to power delta n. Okay, so this is it for the today's video. If you like the video, then please hit the like button and please consider subscribing. This is Mohit Gupta signing off. Have a great day.